In this tutorial, we're going to interpret graphs that involve momentum. And I'm going to explain everything as we answer the questions. Question A. What is the impulse from 0 to 4 seconds? We need to check our variables first. We have the force here. The vertical axis is the force in newtons. And then the horizontal axis is the time in seconds. Right, so we want impulse. How can we get impulse from force and time? Remember, we said that F net times delta t is equal to change in momentum, which is impulse. This is the impulse. So it means if we multiply force and change in time, we'll get impulse. Right, how can we do that in this graph? Usually I check using the rectangle. Right, if I draw a rectangle on this graph, the vertical axis is force in newtons, and then the horizontal axis is time in seconds. And then if I say force times time, that's area. You see that? Force times time, that's area. So it means the area under the curve or under the graph will give us impulse. So you must check these things. Your points of intersection where your graph cuts the x-axis. Check the gradients, the meaning of the gradients. Check the area under the graph. For impulse, we're going to find the area under the graph. That would be force times change in time. Net force times change in time. But now, the shape we have here is a triangle. So we're going to use the area of a triangle, which is half times base times height. Our base is 4 seconds, and then our height is 4 newtons. So it's going to be half times base, which is 4 seconds, or newtons, 4 newtons times 4 seconds. Do you see that even the units are coming from this? Because the units here for impulse is newton seconds, from newtons times seconds. Right, so it's 4, then we get what? We get 8 newtons seconds. And then let's go to question B. What is the impulse from 4 seconds to 8 seconds? Here, 4 seconds to 8 seconds. Again, we have a triangle. Here we say that the impulse is 8 newton seconds. Okay, and then what about here? These triangles look congruent, they look the same, so their areas must be the same. But the distance from 4 to 8 here is 4, 0 to negative 4 is 4. But consider the direction. Now it's in the opposite direction. So it means it's going to be half, since it's a triangle, times negative 4 times 4, which is negative 8 newtons seconds. Now, if you check, the magnitude is the same. What is the difference here? The difference is direction. Let's move on to C. What is the change in momentum for the interval 0 to 8, from here up to there, 0 to 8? Here we found that the impulse is 8 newton seconds. And then here also we found that impulse is negative 8 newton seconds. Remember, impulse is change in momentum. Remember that from the impulse momentum theorem, right? Impulse is change in momentum. So now what is the change in momentum for the interval 0 to 8 seconds? So we have this plus this. So it's going to be impulse from 0 to 8 seconds is equal to 8 newton seconds plus negative 8 newton seconds. Then what do you get? You get 0 newton seconds. If you're using the force time graph, area under the graph gives you impulse, or area under the graph gives you the change in momentum. And then D, what is the impulse of the interval 8 seconds to 24 seconds? 8 seconds to 24 seconds. So what we have here, we have a rectangle. We're going to find the area of this part, and then we have a rectangle also there. We're going to find the area of this part. This will give us what? The impulse. Okay, right. But now let's start with 8 to 16. From 8 to 16, that is 8 seconds. Or let's start with newtons. But now it's going to be negative 4. Negative 4. then times from 8 to 16, that's 8. And then we get what? Negative 32 Newton seconds, right? Then we come to 16 to 24, from here up to there. The newtons is 2, and then the time 16 to 24, that's 8 again. So it's 8, which is 16 Newton seconds. Now the impulse, total impulse now, that is from 8 to 24. You can write 8 to 24 here is a subscript. Negative 32 plus 16, which is negative 16 Newton seconds. So what does that mean? So it means this is 16 Newton seconds in the opposite direction. This was the force time graph. What about the velocity time graph? Right, let's look at this example. This is the velocity time graph. Okay, from the velocity time graph, what can we get? We can get the initial velocity and also final velocity. Okay, we can also get the change in time, like 20,1 to 20,2 there should be 0,1. That's change in time. Initial velocity for x, which is 8 meters per second, and then final velocity, which is 4 meters per second. Since we are dealing with momentum, we may need only this. Remember, momentum is mass times change in velocity. Trolley X of mass 1,2 kilograms travels 8 meters per second east and collides with trolley Y of mass 0,5 kilograms, which is initially at rest. The velocity time graph below shows the velocity of trolley X before, during, and after the collision with trolley Y. Trolley Y has a mass of 0,5 kilograms. Calculate the magnitude of the velocity of trolley Y immediately after collision. Right, let's check the information that we have. We have the mass of X, which is 1,2 kilograms. We have the initial velocity of X, which is 8 meters per second. We have the final velocity of X, which is 4 meters per second. Right, okay. Then change in time, which is 0,1 seconds. Then for Y, we have the mass of Y, which is 0,5 kilograms. And then the velocity, we don't have the final velocity. That's what we want. We want the final velocity of Y. That's what we're looking for. Y is initially at rest, so the initial velocity of Y is equal to 0 meters per second. Right? Then the direction, let's make east, positive direction. Let's say east. Now we can use the law of conservation of linear momentum to solve for this. So the mass of X times the initial velocity of X plus mass of Y times initial velocity of Y is equal to mass of X times final velocity of X plus mass of Y times final velocity of Y. That's what we're looking for. Right, let's substitute what we have. So we have 1,2 times 8 plus 0,5. Then initial velocity is 0. Then is equal to mass of X 1,2. Then times 4 because it's moving east. So velocity is positive plus 0,5 times the final velocity of Y. Right, so now the final velocity of Y is going to be 1,2 times 8, 1,2 times 8 plus 0,5 times 0 minus 1,2 times 4 divided by 0,5. And then we get that the final velocity of Y is 9,6 meters per second. Since it's positive, so it's going to be east. Let's look at question B. Using the same information, calculating the magnitude of the average net force that trolley X exerts on trolley Y during collision. Right, we say that our positive direction is east, right? And then F net times delta T is equal to change in momentum, right? We say this is 0,1, isn't it? So now we substitute what we have. So F net times 0,1 is equal to change in momentum. Change in momentum, so it's mass of x, which is 1 comma 2, and then mass times change in velocity, that's momentum, that's change in momentum. Then it's going to be final velocity, 4 minus 8, because here is 4, here is 8 meters per second. And then what do you get? F net is equal to 1 comma 2 times negative 4 over 0 comma 1, which is negative 48 newtons. So now F net is equal to 48 newtons west. And then this last graph, we talked about this graph in one of the examples. It can be momentum versus time graph, right? What can we get from this? You can get your initial momentum, you can get your final momentum, okay? And then the gradient, this is change in momentum over change in time. Remember, F net is equal to change in momentum over change in time. So meaning that the gradient will give you your F net, okay? Remember that. And then also you can get your delta T here, right? So these are some of the graphs that you can get. We discussed what? The force versus time graph, the velocity versus time graph, and the last one, momentum versus the time graph. This one, you can check the examples under impulse. We did this.